We continue with the theorem 3.2.2 in order to build up finite dimensional vector spaces. So this theorem states that suppose we have two lists, L with vectors w1 through wn, and list M with vectors v1 through vm. And notice the different index, the different number of vectors. L has n vectors, M has lowercase m number of vectors. And then we know that L spans the vector space V. We call this then a spanning list if it spans the whole space. And M is linearly independent in V. Then the theorem states that M should be less than or equal to N. So if you look at what N and M are, so basically what it says is that spanning list L cannot be shorter than any linearly independent list. So to span a space you need to have a certain minimum number of vectors. Or you can turn it around and say that a linearly independent list cannot be longer than any spanning list. You cannot have too many vectors in a linearly independent list. At some point it becomes dependent, and it will be sooner or at the same time where you get a spanning list. So this is related to how we can build up bases very soon. The process of we manipulate the list L by adding and subtracting vectors. And to see the proof, first note that M is linearly independent, and we saw this before that it cannot have any zero vector in it, because zero vector makes every list dependent, linearly dependent. Alright, so starting with L, we have W1 through Wn elements. This spans V. That means we can add V1 to the beginning of this list, and V1 itself in V. V1 is the first vector from M, so that means V1 can be spanned by W1 through Wn. So if we add this to the beginning of the L, V1, W1, Wn, we get a new list. But that means that this is linearly dependent. So this is V1 is not zero, and it's in the span of these, since W1 through Wn spans the whole space. So that means this is linearly dependent. Since we can span V1, we can get V1 as a linear combination of W1 through Wn. We can rearrange this equation. V1 equals sum of Ci Wi, I equals 1 through M, N in this case. And we can rearrange this and get a non-trivial linear combination minus V1 and then plus the sum. So this is a non-trivial linear combination that gives 0. And by definition, if you have a non-trivial linear combination that gives you 0, then that list is linearly dependent. Alright, so if we have a linearly dependent list, then the previous lemma, the linear dependence lemma, states that we can remove one of the vectors, and the index is supposed to be larger than or equal to 2, so that means one of the w's can be removed. And the remaining list is still a spanning list. That's also part of the linear dependence lemma, that the span doesn't change, and the span is still the whole V. After that we add V2 to it, so we will have V1, V2. We don't know which w's we have, so let's renumber the w's, the remaining w's with w prime, but then now we don't have n, we have one less, we have n minus 1. And again, what we have is that this becomes now linearly dependent, which means that again we can remove one of the vectors. So we continue this process. Let's say that at one point we have, after we continue this process of adding and subtracting vectors, let's have a notation for this list B with vectors v1, vj added to it, and then w1 prime. So we removed one of the w's already, so let's say that we have w n minus j prime at this point. So now we add, and this spans v. So now in the next step we add vj plus 1. So what we get is v1 vj plus 1 w1 prime wn minus j. So this is then linearly dependent because we added an additional vector to a spanning list. Then we're supposed to be able to remove, again by the linear dependence lemma. So one vector can be removed, and the linear dependence lemma had three equivalent parts. So one vector that can be removed to have the same span was also linear combination of the previous ones. So this is also linear combination of the previous ones. And because the VJs are linearly independent, since these are from list M, none of them can be expressed as a linear combination of the previous ones. So the one that we can remove, which is also a linear combination of the previous ones, cannot be any of the V's. That means that we can only remove a W. Let me summarize this process. After adding a V vector, we can always remove a W vector. That's basically what the process established. After adding a V, we get a linearly dependent one, and by the linear dependence lemma we can remove one, and it must be W that we can remove because the V's are linearly independent. That means that we can always remove a W. After adding a V, we must have the same number or more W's than V's. And the number of W's should be larger than or equal to the number of V's, which was n. And this is exactly what the theorem stated. So at this point we had some examples already for vectors that were spanned by a few vectors. Let's classify all these vector spaces through a definition. A vector space V over the field F is called finite dimensional if it has a finite list that spans it. So we call this a finite spanning list. The next theorem, 3.2.3, is about subspaces. We already saw many examples of subspaces and how important they can be. If U is a subspace of a finite dimensional vector space V, then U is also finite dimensional. We will prove this. If V is finite dimensional, then that means that it has a spanning list which is finite number. Let's say W1, W2, Wm is a spanning list. Case 1, if U is the subset of only the zero vector, it's called a trivial subset, then U is the span of an empty list. And if you have an empty list that has a zero number of vectors, which is finite of course, so the proof is done for this case. So the only reason we treat this separately because we don't want to work with a zero vector, especially if we talk about spans. Case 2 is that U is different from the trivial subspace of zero vector. So if it's not just the zero vector, then that means that there exists at least one V1 non-zero vector in it, in this subspace. Then we check whether or not the span of this equals to the whole subspace. If this is the case, then that means that one vector spans U. That means it has a finite spanning list. So that means it's finite dimensional. we are done. U is finite dimensional. If the span is different from U, then there exists V2 such that V2 is in the set U, but since it's not just the span of V1, that means it's outside. So this is a set minus notation. I think we use it the first time in this class. It's in the U, but not in the span of V1. And also V2 is different from 0. So then what we have is that V1, V2 is a linearly independent list. Here again we use the linear dependence lemma, because if it was linearly dependent, then the lemma says V2 could be a linear combination of V1. So then we check again what the span of this list, V1, V2, and if the span is this whole U, then again we have that U is finite. And if it's not the case, otherwise, if the span is not the whole subspace U, then we can choose again another vector, V3, which is in U but not in the span, since we know that there must be some other vectors in U that are not in the span of V1 and V2. Again, what we have is that V1, V2, V3 is a list that is linearly independent according to the linear dependence lemma. Otherwise, V3 or V2, well, we already know that V2 cannot be a linear combination of the previous one, so that means V3 would be a linear combination of the previous ones. But that's again not possible because it's in U but not in the span of V1, V2. So this is a linearly independent list. This is actually in U, but U is also a subspace of V, so that means it's in V also. So we keep adding these vectors, and at one point we have V1, Vn vectors, say, which is still linearly independent, and this is in V also, not just in U. And what we have is that according to the previous theorem, this cannot be longer than the spanning list. And the spanning list was W1, Wn, which means the process of adding vectors must stop at some n less than or equal to m step. How can this process stop? Well, we did this addition when the span was on the whole space. So this process will break down only if the span will be the whole subspace. So the V1, Vn equals to U. That's how it will stop. And this shows that U is finite dimensional. Now the big definition of this section is a list L, V1, V2, Vm is called a basis for vector space V if L is linearly independent spanning list. So this process in this theorem, where we keep adding vectors, theorem 3.2.3, what this says is that all finite dimensional vector space has a basis. We just start with a non-zero vector and then we keep adding vectors, and at some point we get a spanning list. That's the process. Process to create a basis. Start with V1 not equal to the zero vector. Check if span of V1 equals to the vector space V. If yes, then V1 is a basis, and if no, that means the span of V1 is not the whole space. Then we can choose V2, which is in the space V but not in the span V1, and then we add this V2, and then we continue this process. And the theorem says that at some point this process will stop and you get a linearly independent spanning list. Let's see an example, very simple example. Again, in R2, as usual, we want to create a basis. Okay, so let's start, for example, with vector V1, which is, let's say, 1, 3. Then we check what the span of this vector is. So that means the all the possible linear combinations of V1, but if you have only one vector, the linear combination is just scalar multiples, where A is in R, scalar. So another way to write this is that this is A1 times the vector 1, 3, where A1 is in R. Then to see what this really is, how this looks like, we multiply through, we get A1, 3A1, A1 is in R. Since the first component A1 is actually the X component, maybe it's useful to write this as X, 3X, rename the scalar A1 to X. That's just a different notation for the same thing. Another way to write this is that this is XY vectors such that Y equals to 3X and X is in R. The Y equals to 3X is a straight line in R2, and that means that this is not the whole space V. It's only a straight line going through the origin. This is the span of V1, and V1 is the 1, 3 vector, and the span is just a scaled version of this vector, all the possible scaling. Then in this previous theorem, the process was to now choose V2, which is in V but not in this span of V1, which means that we have to choose V2, which is in R2 but not on the straight line, so it's minus the span of V1. So we of course have infinitely many choices. Just for fun, let's choose the vector 2, 1. V2 equals the 2, 1 vector as an example, and then we check what the span of V1, V2 is. So the span A1 times V1 plus A2 times V2 such that A1, A2 are from the set of scalars, real numbers. That's what the definition of span is. Let's write down how this looks with our specific vectors. So A1, the first vector was 1, 3, plus A2, the second vector is 2, 1. If you multiply through the vectors with the scalar, we get A1, 3A1 plus 2A2, A2. Now I could leave this notation, it's really just a notation, but at least at the beginning it's useful to change the notation from A1, A2 to X, since that was one of the first coordinates, and maybe Y could be another scalar notation. So let's say X, 3X plus 2Y, Y, and here X, Y are real numbers. Another way to write this, of course, is we add together the two vectors, and we get X plus 2Y and 3X plus Y, such that XY is in R. The question is now, is this equal to the whole R2 or not? Another way to ask this question, can all vectors AB be written as AB equals X plus 2Y, 3X plus Y? If I rearrange this equation, writing as X plus 2Y, 3X plus Y equals to AB, I can also write this as a matrix vector equation. So if I separate the X and Y into a column vector, then we just have to collect the coefficients 1, 2, 3, and 1 into a matrix. So it's matrix times XY vector equals to AB vector. And then this 1, 2, 3, 1 matrix is in fact invertible. You can check that. For example, the determinant from undergraduate linear algebra. The determinant of 1, 2, 3, 1 is cross multiply, and you get 1 minus 2 times 3, which is minus 6, so this is minus 5. The determinant is not 0. For example, that shows that it's invertible. That means that we can solve for xy as 1, 2, 3, 1 inverse AB. And this can be solved for all AB, which means that all AB in R2 can be represented as x plus 2y, 3x plus y for some xy, which means that all AB is in the span of V1, V2. So the span of V1, V2 equals to the whole vector space R2. That means this V1, V2 is a basis. We created a basis, linearly independent list, and it's a spanning list. We still have a few more things to cover in this section. The next lemma, 3.2.5, says that if V is finite dimensional, then there is a unique integer n greater than or equal to 0, such that all bases have length n. And we call this number the dimension of V. And the notation is that dim V equals to n. And of course, from undergraduate studies, we already know that this is why we have the notation R2 for the two-dimensional Euclidean vector space with two basis vectors. But probably, for example, you saw a basis different from the special basis 1, 3, 2, 1 vectors V1, V2 that we looked at here. Usually we look at the standard basis. We can have many different bases. This lemma says that if you have a basis with length 2, then all bases will have length 2. Another simple lemma, 3.2.6, says that if you have a basis L with L equals to V1, V2, Vn, so that means also that linearly independent, and the span of L equals to the whole space, then, and only then, all vectors in V have a unique representation as a linear combination of the basis elements, basis vectors. So a more compact way to write this is that for all vector V in the vector space V, there exists a unique, so the notation is this existence notation with the exclamation mark denoting unique, coefficient Ci in the scalar field for I going from 1, 2 through n, such that the V vector can be written as the linear combinations of the V vectors with Ci coefficients. Based on this previous lemma, that was actually a consequence of a theorem. We had this process of creating a basis where we started with a non-zero vector and added more and more vectors to it. The next theorem shows that we can do this in an opposite way by cutting down a spanning list until it's linearly independent. This is theorem 3.2.7. If L list V1, V2, Vn is a spanning list of V, then a basis of V can be obtained by deleting certain vectors from L. So this is also a very convenient way to create a basis. You are just throwing out some vectors that are not necessary. So let's see the proof of this, since this is a process that we're going to talk about to create a basis. The first step would be to throw out all zero vectors, of course. So a spanning list, it doesn't say that it's linearly independent list, and of course if it's linearly independent then it's a basis, so it's definitely not supposed to be linearly independent. So it might have some zero vectors. Throw out all zero vectors. Then we get a new list, L prime. Case 1, we left with empty set. Then that means that V is the span of our empty list. and that means that this is just the zero vector itself. And we know that the empty set is a basis in the zero trivial vector space. We are done. Then case 2, if we have a non-zero vector in the list, still what we have is, after throwing out the zero vectors, still we must have a spanning list. So we still have that span of L prime equals to V. Then we have a subcase that L prime is linearly independent. It's a spanning list, then that means it's a basis of V. And again, then we are done. Then if L prime is linearly dependent, that means that we still have too many vectors in it. We have some vectors V1, but it was originally V1, V2, Vn. So let's say we have V1 prime and some Vn prime list, linearly dependent. Then we have the linear dependence lemma, which says that we can throw out one of the vectors and still have the same span. We can remove V prime j and still have the same span. But this span was V, that means we get a shorter list and still have the same span. Let's denote this with L double prime. So what we have is that the span of L double prime equals to the span of the previous one, and that was the whole space V. And again, we would have two cases. If it's linearly independent, then we are done. Or if it's linearly dependent, then we can throw out a vector using the linear dependence lemma. Now you can see how important this linear dependence lemma was. In each of these steps, we have a spanning list. So that means that we cannot just throw out all the vectors. This process must stop when the length of the list equals to the dimension of the vector space, since we cannot have a shorter spanning list than the dimension. And the reason why we have to stop is because we have a linearly independent spanning list, which means a basis.